Well, greetings, everybody. Thanks for dropping by. Greetings from sunny California. I am seeing lots of people here who are in colder places, and if you can do it, in the space where your name is, type in where you're calling from. Well, actually, the way you would do this, or the way I would do it if I was going to do it, my name is so long you can't see California anyway, but you click on your name, and it allows you to edit your name. So, if I were to click on my name, I could change I used to change my name sometimes to Oz the Great and Powerful, but I won't do that today. All right, today we're going to talk about coding in the Physics First modeling classroom, and so I just want to lower expectations a little bit and say that that I am not actually coding in a Physics First modeling classroom because, alas, I have no classroom anymore. So what you're hearing is secondhand information, but it's kind of an exciting initiative, and so I'm going to tell you what we're doing and what we hope to do, and I'm going to ask you some questions too about what you think we should be doing, because ideas will make this better. And what we're doing is called design-based research, and when you do design-based research, you do it because you think things will emerge, not because you want to test some hypothesis, but you think good things will emerge, and I think that's just kind of the nature of the modeling community. So, as I say on my screen here, if you can see the screen, I like interactive webinars, so please just turn your mic on and ask a question if something comes to you. And then be sure and answer when I ask questions, because that's what keeps me coming back. All right, so I didn't make slides. I made a Google Doc that I can scroll. We've used computers, modelers have used computers for 30 years to collect data in our science classrooms. And so our kids know how to do that. You can see this old kid in this photo here. This is a pretty old photo, really. Getting ready to skydive. I'm wearing my Skydive Arizona t-shirt there. And I'm all rigged up with vernier sensors to collect some data on the way down. So so we've been doing this data collection thing for a long time, but we really don't know what happens. We just have this little, we have inputs in the case of the skydiver. You've got some sensors there that are inputting altitude data and pressure data, and magic happens and it comes out on the screen. And so when we talk about computational thinking, and in particular when we get at computational thinking by having students actually write code or read code or modify code, is to kind of get inside that black box and take a peek at the processes that are going on and try and understand those processes. So last year about this time we wrote a grant to the National Science Foundation. We did this in cooperation with the American Association of Physics Teachers and with STEM Teachers NYC, and with the American Association of Physics Teachers, and with the Bootstrap project. And Bootstrap is some computer scientists in New England. They're at Brown University in Providence, and they're also at UMass Amherst and at several other schools that they actually write computer languages, which is kind of interesting, to work with people who have written the computer language that you are working with they use their languages, some of their languages right now, one in particular to teach algebra. So they have made a concerted effort to create computer languages that are accessible and usable by middle school students, which is where their algebra initiative is targeted at 7th and 8th grade. So we met them at an AAPT meeting and thought, you know what, we have this common interest in making computational thinking and computing in particular a little more explicit in physics. So what shall we do? The goal of this proposal is to really understand how computational thinking can and should be fully integrated into the physics classroom. And we decided we would start with the physics first classroom because the physics first classroom theoretically includes all students. It's a required course rather than an elective. And so it's going to have the broadest possible reach in terms of English language learners and high needs students and pretty much the gamut of what will show up in our high school classroom. And if it works for all those students, it should work for those, those 3 cone-headed boys in AP Physics. So our deliverables for this grant are a fully functioning modeling physics workshop that is computational modeling and physics first, primarily. A tested and refined set of curriculum resources for the workshop that can be used in physics first classrooms. An attitude survey for both teachers who are in the workshop and for their students, an attitude survey toward computational thinking. And then finally, an assessment that's really a physics assessment, but it's a physics assessment that asks students to use a perspective of computational thinking, that requires them to use a perspective of computational thinking to respond to survey items. So we have 3 years to do this, and $1.25 million. And it might sound like a lot of money, but it's not a lot of money. Yeah. The bulk of that money is going, by the way, to teacher participants. The money that we can actually use. There's money that ends up going for logistics stuff and for accounting stuff. And when all is said and done on a grant of this size, you're lucky if you have 2/3 of the money they say they're giving you. And that's pretty much the case in this grant. By the way, for those of you that are just joining us, welcome. We are delighted to see you, hear you in this case. And if you have a question, just turn your mic on and ask your question. Don't wait until it's time for questions, because I'm hoping that there will be questions generated throughout our call. And if you're not speaking, though, it's nice to have your mic off in case there's like dogs or children there.
I do have a quick question, Colleen.
Sure.
I'm curious about the scope of the curriculum that you're designing. Is this intended to be a complete physics first course with the computational stuff integrated in throughout, or is this an auxiliary curriculum to be added to existing physics first courses?
Really good question. At the moment, we are using the physics first course curriculum that we developed for Michigan a year ago they sort of changed their mind and decided that they really just wanted a physical science course. So we are redeveloping that now, so it's more of a physical science course. But we have taken the physics first curriculum that we developed for them and rejiggered, not all of it, because we couldn't do it all. So I should preface this by saying we started this last year. Actually, we started it last summer. We didn't get the money from NSF in time to pay for last summer, but we had a grant from an organization called 100K in 10, which stands for 100,000 highly qualified teachers in 10 years. They've been working at it for about 5 years, and but 100K in 10 gave us a little bit of money so that we could get started last summer. So what we did was we took that physics first curriculum, and kind of rewrote the teacher notes and rewrote a bunch of the activities so that they used computational modeling as part of their activities. As with any first draft of anything, using these materials this year, and the people who participated in that workshop last year are using these curriculum resources this year in their classroom, we've discovered that we need to do a second draft. But the goal is to have, just like you have, you can download the physics resources from the website or download the chemistry resources from the website and use them pretty much as they're written. That's what this will be when we're done. We're on our way, but we've only done 5 units. And, we've done enough units to run a workshop, but after having used them for a year, or most of a year, the teachers that develop them feel like, no, there are substantial changes that need to be made. So aren't you glad that we didn't just throw them out there and say, hey, try this. They will be tested when they're released for public consumption. That's actually a question, though, that I'm going to ask you a little bit later about at what point people are feeling strong and brave enough to maybe begin interacting with this stuff. So moving right along. Why are we doing this? Well, there was a call in I think it was 2015 or maybe it was early 2016. It might have been in Obama's 2016 State of the Union address that he sent out a call for computer science for all. And he said to empower all American students from kindergarten through high school to learn computer science and to be equipped with computational things, they need to be creators in the digital economy and not just consumers. So computers have been around a long time. We don't get the best out of them in general in education. And I don't know. It takes a long time for educational institutions to change. This is not news to anybody that it's going to take a while to introduce new technology in an educational environment, and it's not just cost. The teachers have to be comfortable with it, and they have to be confident that they can use it. And this initiative is no different. I couldn't teach computing to my students. I learned a code, 10 years ago, 12 years ago, something like that. I took the Matter and Interactions course that Bruce Sherwood was offering online from NC State, and it was an awesome course. And I was surprised and pleased that I could actually learn to code in VPython. And I thought, wow, you really can teach an old dog new tricks. But I could no more turn around and teach that to my students than, fly to the moon. So there's a learning curve involved in being able to teach something to someone else. And if teachers never learned programming in school, then we can't expect them to teach programming to their students. So that's part of the lift, the heavy lift for this project. And I'm happy to say that, you know, we see the teachers involved last summer moving along that learning curve nicely. But it's kind of like being a new modeler. I know when I was a new modeler in my first year of teaching using modeling instruction, even though it was my 15th or so year of teaching, I sucked. I couldn't, you know, it was just really hard to get it down to a nice flow. And in my second year, I was much better. And in my third year, I think I was good. It's going to be the same for coding. You know, if you've never done it with students, it's going to be rough in the beginning. We have to be strong and be able to persist. This is something the modeling community does really well. We help each other be strong. We help each other persist. And so I think this is why we are really well positioned to bring this in an almost an institutional way into physics classrooms. So I'm excited that we're kind of leading here. All right, so we used physics first because it has the potential to reach all students, not just the motivated ones. And as far as National Science Foundation is concerned, whatever you propose has to have the potential for broad impact. And so this was a broader impact, you know, gold star for us. Learning to code for students seems to be not only motivating, but also could be beneficial to them in other classes. And finally, learning to code, we see that it improves their mathematical thinking. And there's research to back that up. There's just not research that's, you know, like down at the 9th grade level. So any questions so far? Well, here was one of my big questions. What is computational thinking? What the heck do we mean when we say computational thinking? We say, you know, it's in the NGSS, Science and Engineering Practices, that students will do mathematical and computational thinking in our classroom, and we say, check, we do that because, hello, it's physics. They compute things. So check that one off. Well, that's not all there is. There's more to it than that. So a couple of years ago, a group of computer science education researchers at Chicago, some university in Chicago, made a concerted effort to figure out what computational thinking is, and in particular what it looks like in mathematics and science. So I'd like you to take a moment and just look at this table that they prepared. There are data practices, there are modeling and simulation practices, computational problem solving, and systems thinking. So take a minute and look and then tell me what you think. And I actually made this presentation on a Google Doc so that I could take some notes about what you think.
Colleen, this is John.
Yeah.
I mean, I'm looking at this list, and what comes to mind is that this is just another tool. All of this, you know, you can slice and dice it and get in between this and that. But if you zoom out and look at it all, this is just another tool, a tool that we could use a lot. That in physics, it does a lot of different things on a lot of different levels. it can have a lot of moving parts. But aside from all that, when you zoom out and look at it as a whole, it's another way to to do physics. It just really is, with the aid of technology. That's what I see, and reminds me of a time when I took a course at ASU with Bob Culbertson. I know I'm getting his name right.
Right. No, that's right.
And anyway, he actually did some modeling of systems with Excel, and he actually showed us the code, and he showed us how it made a system work, and it was actually really cool. And I'm going back 10 years ago, if not longer, and I'm thinking this definitely could be used in a physics classroom. I mean, and just one more point. I mean, I think about how I see kids struggling with motion maps a lot when we do kinematics. Mm-hmm. I know what they're supposed to do. They're supposed to slow down your thinking and get you to really, examine things. But it would be really neat if, for example, you could get the kids to write code so that the code could draw the motion map, which I don't think would be impossible to do. I mean, I've always wondered, why can't we get them to write code that would actually construct a motion map? You set up the parameters, that again, it's a tool to do something like that, because I see them struggling with the motion maps because but in the struggle is how they learn to make the connections. So that's my 2 cents.
Yes, those are excellent. That's actually at least 5 cents, John. That was awesome. It's interesting that you mentioned motion map. That was one of the first things that we asked the Bootstrap people for in our workshop last summer. So when we had our workshop last summer, the way we structured it was we spent the first week learning how to code in their integrated development environment, which is called Pirate. And Pirate
okay, yeah, I've heard about them.
Yeah, so we use Pirate, and they chose Pirate because it's Python-like, but it has some really good supports for students to make error checking not so horrendous. Which is important, because if you want your students to experience success, you don't want them to get depressed when they get an error message. And that's actually come out really strongly in this whole project as a topic and as a way of approaching making sense of things. We're still really driven by the need to have a right answer. And so we want to solve problems, and we want the answer to be 8.8 meters per second or something. Or we want the right answer to be this perfect parabola. And if it doesn't happen for them, they get depressed, and sometimes they quit. And so dealing with that has been, and I think this is one of the project outcomes, that even if nobody ever does any coding with their students in physics, if they learn to look at problems and the process of arriving at a solution in a different way, then we will have made a contribution. Errors are good.
But that is de-emphasizing the answer and taking more time for the answer. Sounds like your other responder just said that that's what this computational thinking is going to do.
Can you say some more about that? What is de-emphasizing the answer? The error analysis thing?
Getting kids to not take the shortest line between question and answer, because they want to find the shortest answer, and forcing a process that you're talking about sounds to me like a good opportunity to meander along the way to the answer. Hopefully getting the right answer, of course, but it's not only the answer. I'm finished. Next question. What's the answer? Next question.
Right, right. Well, a lot of it, too, is going to have something to do with how we ask questions. If we ask questions that can be answered with a single word or a single, quantity, then we're going to funnel them down into that way of thinking about what doing physics is. So, and one of the things that coding allows us to do is to see doing physics as physics do, because physicists do computational model for sure. Then maybe they'll have a different idea about what physics activity is. So getting back to our list up here, data practices, modeling and simulation practices, computational solving, problem solving, and systems thinking practices. Anyone have any other thoughts about this list? Is it complete? Is there stuff there that doesn't belong there? Does it suggest any way of thinking?
Colleen, can I speak again for a minute?
Go ahead.
Yeah, real quick. Next year I'm going to be teaching the new AP Computer Science Principles course, and a lot of what you're doing as you were explaining the process of what you're trying to do, and the goals for students, that's the College Board's goal. What the launch that they did this current school year with AP Computer Science Principles was the largest launch ever of any new course that they ever introduced. They have so many people on board. They've never had that happen before. But all of what I'm looking at in these tables and lists, it's all in that course. All of this. And but that's a course. It's an AP course, but it's designed. They don't even tell you what language to use. And they also, all you need to have is algebra, a decent background in algebra. There's no other requirement to take this class. You do not you can have no experience in coding whatsoever. So a lot of what I'm seeing here, they're kind of kindred spirits, so to speak.
Yeah, cool. Well, that's really good to hear. We had 4 computer science teachers in the first week of our workshop where we were learning Pirate from the Bootstrap people. They invited 4 computer science teachers to just sit in and kind of refresh their understanding of Pirate. They were already kind of familiar with it, but I felt like there was a really different mindset between computer science teachers and physics teachers about, why we use computational tools. Would you agree?
I guess so. I mean, John, again, I don't mean to dominate the response here, but I would agree, only because I think it ties into some other themes, like there's a certain level of math phobia, there's a certain level of physics phobia. So I don't want to say too much more than that, but yeah, I think there is a difference. Physicists tend to go in a little bit different direction than the other sciences. I think just by the nature of the kind of a discipline that it is. So,
right.
I think we're all scientists, but we're also different. So I'll leave it at that.
So what I noticed with these teachers is that for them it was all about coding and writing good code, and there was this coolness of being able to see what you see afterwards, but they weren't. It didn't appear to me that they were trying to learn anything about what they were doing. About what they were producing. In other words, they weren't writing code in order to learn about concept. And so, and for the
Can
physics
I interrupt
teachers
you for
in
a
the room,
second?
pardon me?
Excuse me. Isn't it good that they were writing code? You said they were writing code not to learn about code, but not to learn to write the code, but not to learn about content.
Right.
Is it?
Right.
Aren't we wanting kids to get lost in that process of not going for the answer? Let them play a while with the code. I miss what was bad about that. If you would.
It's not bad. It's just that it was like context-free
Okay.
learning. So,
Okay.
so it's like sometimes when you're learning math and you don't know where or how that math might apply, it's like you get so tangled up in the procedures or the syntax in this case that the usefulness of what it is you're doing escapes you. And so for the physics teachers in the room, I felt like they were all about, what does this buy me? What use is this for me? And particularly, what use is this for me in understanding physical systems? And my impression of the computer science teachers was that, they thought that was really interesting and an unusual way to think about computer science, because they didn't feel context was that important.
Colleen, if I may interject, I think that's just a bias in a sense. Math teachers, I was initially a math teacher, and you're in it for the math, and computer scientists are in it for just the specifics of the discipline in and of itself. And, people come at things from different places, and I think, not that that's necessarily bad, it's just what it is. And I think some physics teachers would look at coding and say, I've got my hands full now. I don't want to add complexity to what I already am trying to do. There would be that attitude as well. So I don't know. I think that I see the point where, and that can be a buy-in. You tell the kids that know how to code, well, let's use it for something. Other than the fact that it's just you have the beauty and joy of computing it in and of itself, but then okay, let's see if we can use it to do some useful things. Right.
Make something happen. And I think that was sort of the perspective of the physics teachers in the room, and I think the computer scientists didn't, they didn't marginalize that perspective as wrong or inappropriate. It was just like something new to think about because they'd never really considered it in that way. So I thought, okay, so now we have this table of or taxonomy of computational thinking. This is written by computer scientists who are fine people, and we partner with some really fine computer scientists on this project, so I don't want to give the impression that I don't think that they're good or doing good work. But how does this translate into teaching? Is this a learning trajectory? Is this a sequence? Is it even complete? Or is it just a collection of practices?
If I can add a little bit to that, I think that from what I've seen, when we can get kids to think computationally, somebody earlier mentioned about the fact that it's the kids want really badly to go directly from point A to point Z and skip as many steps as possible to get there. And what I've seen with kids programming, particularly when there's some particular goal in mind, not necessarily an absolute, it has to be exactly this program, but they start off with a level of frustration because the computer will do exactly what you tell it to do, but that forces them to be more careful in what they do as they do it. And I don't have data to back this up, but I feel like I've seen students actually are then more careful in the work they do outside of the computational stuff in my class, which I think is a pretty important part of why I keep doing this computational stuff.
And actually, we are finding with the teachers who developed the stuff and are using it in their classroom this year that that's exactly what they're finding. And that they are that sometimes phrasing things as error messages, or I mean, they have it has transformed student attitudes. And one of the things that we were worried about was that this would just be, too heavy a cognitive load for many students, and they are eager to embrace that cognitive load. So, we were
Yeah, if
worried
anything,
it's not a worry.
if anything, my criticism of the diagram you've got displayed on there would be it doesn't communicate at all the sort of exciting benefits of computational thinking, of programming, and of making a computer do something that you have personally told it to do. I see that show up in my students' eyes because they've used computers to do tasks before, but it's always been somebody else's program that someone else wrote to do things the way that someone else wants them to be done. And this giving them control over the computer in a much deeper way gives them a different view on what computers really are and what they can do.
Yeah. It's they get under the hood and they see it's not that hard, but it is very taxing, very demanding, very particular about what it will accept as inputs. Okay. Any other thoughts, questions, comments, concerns about this framework? Okay. Here's what we're going to talk about now. So we had this identity issue for ourselves. How do we explain what we are doing to others? Because it turns out many places that school districts or systems are very concerned about computational thinking and about computer science and about getting computer science into K-12 and what should that look like. And they're really struggling with, there's just no time. Teachers tell us there's no time to do anything. We can't add another thing to our teaching day. There's just no time to do it. And so in trying to, explain what we're doing, that we're not teaching computer science instead of physics. We're not, this is not a course in learning how to program. This is a physics course and we're learning physics. But programming is one of the activities that we do in order to make that happen. And so we, and this is a really, I'm just going to tell you, I'm not good at making diagrams, but it's meant to be like a cable, and you peel back the, layers of the cable, and at its core you find the physics, and wrapped around that core you find modeling instruction, and then wrapped around that you find computational modeling, and wrapped around that you find the development environment that we're using to do this. So, yeah, apologies for the art, and if there's any artists on the call, I'd like to talk to you afterwards.
Is the resemblance to a nuclear core intentional?
Yeah, a little bit. Yeah. Well, yeah, we're physicists. What can I say? We think in certain pictures, right? Pictures that are familiar. So, but yeah, to just kind of try and capture this, we made this little we made this little diagram, and we wonder what you think about it. And there's a cross-section of the diagram over on the left, so you can kind of see, that in the core you have some physics concepts, and then in the outer ring, really, and in the outer ring you see kind of the progression that we move through learning to code, which is first we have them read programs that someone else wrote, simple programs that someone else wrote to figure out how things are working in that program, and then we let them modify pre-written programs, and then and only then do they begin actually writing their own programs. So what do you think? Are we approaching this correctly?
I would say the part on the right-hand side, it's a little bit confusing to me. It almost seems like it intentionally is directly linking energy and reading programs and motion and modifying programs and so on.
Yeah, I think you're right.
As opposed to, that wasn't the message I think you were trying to get across.
It's not, although as it happens, the first 3 units that we developed were energy, motion, and forces. And in the energy unit, all they really get to is reading programs. They may actually do a little modifying there, but we got to modifying and writing really simple programs when we were doing motion with them, and then writing more complicated programs. I'm going to show you one at the end that a student wrote recently, so you can see how good they can get. Yeah, it comes further down the way, but it's not meant to mean these things are locked, and we do need to make those boundaries a little more porous.
Could I add something to this picture? So I would like to be able to see the students go through this cycle of designing, modifying, and reading in each unit. So, because I think students would very quickly get bored if they first have to learn how to read it and then modify, and then at the end of the course learn how to program themselves.
Yeah, it doesn't happen at the end of the course, but it does take, it takes probably 4 weeks before they're actually able to write code.
Okay.
Yeah, but no.
So,
yeah. So this
so
is not,
the motion,
not diagram the whole course either. This is just kind of, yeah, the way it begins. So I'm going to say that reading program space before they actually start writing their own code. It's just the first couple of weeks of school where you're still getting your feet on the ground. And we actually introduced physics first with a qualitative energy unit.
oh,
And
okay.
so that's the unit that's going on when they're just learning how to turn on their computer and call up the pirate development environment and look at the 2 screens and you know, like, kind of see how things work. And actually the very first thing that they write their own code for comes at the end of energy, and they build an image out of pieces, you know, squares and circles and, you know, stars and other things. So, but yeah, this is not meant to be the whole course or even half a course. So it's
How long after? Sorry, Colleen. How long after the start of the course in energy do they make that first program?
You know, it varies a lot, but I'm going to say that the people that did it last year that did this unit with their students were doing it toward the end of the first month of school. And obviously you don't, you know, start day 1, get out your computer, we're going to learn to code this year. There's a lot of other stuff that you're teaching in the meantime. You may do these coding activities a couple of times a week, if that, you know, and everybody does it at different, you know, kind of does it at a different speed. So yeah, maybe 6 or 8 sessions in, they're actually writing their own first code. And prior to that, they're reading it. First, they're reading it, you know, so they've got a pre-written program, and they're going to click on the, you know, they're going to run that program, and they're going to look at the output, and then they're going to read the code and see the output and say, oh, this does this. This made this happen, you know. And after they've done that once or twice, maybe, then they can change a number in that code. or change a color in that code, or change some other type in that code and output that and see what happens. They begin to get an idea of, what instructions you can give a computer that will cause it to execute in this way. So, but then, it's not until they've dabbled with that a little bit that we actually let them write code, and then the first code that they write is very short little things. It's not physics yet. It doesn't get to actually being very much like physics until we get to motion. And, to loop back to someone's comment early on, yes, they can draw. They can and do draw motion maps. So that was something that everybody wanted to happen. We made it happen. Okay, so moving down here. For 2016, we developed qualitative models of energy storage and transfer, constant velocity, uniform acceleration, and forces. There are 8 teachers left from that 12-teacher cohort that are still working with us and that are piloting these in their classrooms. One person dropped out during the workshop. One person ended up not teaching physics. Another person retired, and I forget what the 4th person, their excuse was. But attrition happens, and, this is a lot of work for these teachers. But we're paying them. And we're going to do the same in 2017. So the 2017 development workshop is now full. We've invited all the people that are going to be coming to that workshop. Is anybody that's going to be in that workshop on this call?
Yeah, it's I signed up.
Okay, cool. All right. Well,
yeah.
All right. Excellent. Excellent. We'll be seeing you guys really soon. We're going to be inviting you to our April meeting so that you can meet the old teachers, the old teachers and the new teachers. So these are the curriculum. These 4 are the curriculum areas that we developed last summer. There's been a little of additional development done by a couple of the teachers who were just so captivated by this that they went on writing. But we will start here. We will revise, I think, substantially some of these units, and then do a little more this summer. What I wanted to hear from you all is if there was anything in particular you would love for us to do. And I'm going to tell you what one person is very keen to do that I've already talked to.
Are you planning on adding any electricity and things of that sort?
We have a suggestion to add circuits. We don't have a circuits unit for Physics First yet, but how many of us on this call are Physics First teachers? Let's turn your mic on so that I can take a little count here. Physics First teachers. 1, 2, 3, 4. Great. I want to hear especially from you guys. What should we be prioritizing for this summer? Besides what's already written down here. Is this all you teach in Physics First?
That's all we're able to get through.
Really? Okay. Yeah. That's good to know, because I don't, the other unfortunate thing about this curriculum development project for last summer was that we had almost no Physics First teachers. We said that this was going to be for Physics First, but what we ended up with, because we needed to have modelers, because we're writing for a modeling workshop, so these needed to be experienced modelers, and they need to, they need to be modeling physics people. And within those boundaries, at least in the state of New York, there's not that many people who teach physics first. So we had physics last teachers mostly, and actually that was the root of interesting challenges that I will talk about in a minute, assuming we have time. So if this looks like all of it,
I was just wondering also about optics.
Optics. We don't have an optics unit in our physics first curriculum, but that doesn't mean we never will.
Okay.
So I'm gonna throw that in there. Good. And if you have any other suggestions and you're just shy, please email me. I'm here.
Gravitation.
You have to spell instruction right. Modelinginstruction.org.
I was going to say gravitation is a nice thing to throw in there because you can get the kids to program planetary motion, and it gets them a little bit out of the usual box of just kinematics and forces.
Right, and it lets you get to fields, which I think is really important. We have a little gravitation and forces, but I would second the motion to do a little bit more with gravitation. Great. If you think of anything else, let me know.
Would it be possible to do proportions of maybe sliding scales? I don't really know how we are expecting the student, or what we're expecting the students to program, but if they're maybe developing some graphical tools, because I know in the beginning we do a lot of proportions and scales.
Yes, there's actually some of the activities that have been written have been really aimed at scaling and proportions. So yeah, good.
And I also had a question. Is the expectation that the students make simulations similar to the PHET type of simulations? Or
no.
No. Okay.
No. So they do make simulations, and I'm going to show you one in a couple of minutes. But in general, they are not going to be capable of making simulations that have the same production values as PhET. However, they can make simulations. They can put something on the screen and animate it. Yeah. So yeah, I'm just going to, you know what? I'm going to cut to the end and show you this one really fast. So this is a advanced peek at the pirate development environment. And one thing that Josh is very insistent on, and that his kids have gotten really good at, is putting documentation in their code so that later on when they read it they'll know what it was that they wrote. So all the little red stuff is just comments in the code, and then the black stuff is the code itself, and it's nicely spaced out, so you're going to have no trouble reading it. And I'm not going to let you go through it line by line because we still have a bunch of stuff more to do, but I'm going to run it, and it compiles. And so, wait a minute, it's not React, it's Interact. No, spell it right. Okay, check this out. Can you see what they're studying? It's a projectile. So, and it's a projectile. The code can be manipulated. The assignment was to write code to make Mr. Rutberg throw a projectile, but also to have it be able to be modified so that you can be on different planets. So so this is modifiable code, but that's a student written code, and this is 6 months into the school year. So I was delighted to see that.
I'm really glad to see good commenting and white space in the code. I think that's really good for their practice for the quality of code.
Yes, it is. It's really important, and it's one of the things that that you really have to explicitly drill as a teacher. They're not going to automatically write nice code or comment their code. Even if you do, they're not going to, because they're very goal-driven. So so this is something that they get scored on. Okay, so briefly, the timeline of the thing is that in spring we recruit participants, and next spring we'll be recruiting 20 participants. And so if there's anybody who's interested in being involved in this, is an opportunity for you next spring. We give some pre-testing. We do a 3-week workshop in the summer where we, at least this summer, we're doing development. Next summer, we're going to be doing the beta modeling physics first workshop, computational modeling physics first workshop. So you would be, if you applied for next summer, you would be part of a cohort that is the very first ones to get this workshop, which means it's going to be exciting and rough. But you're going to help us make it a better workshop for the following year. And then in fall, we have follow-up sessions, virtual follow-up sessions to see what's going on. We just get qualitative feedback on how it's going. We have surveys that we do with both students and teachers all 3 years. And then, in the third year, we're going to have, it's not going to be a beta workshop anymore. It's going to be a gamma workshop. But it's going to be a nearly great workshop. And we will, revise and improve each cycle so that at the end of this proposal, this grant project in the end of 2019, this will become a regular part of the modeling workshop inventory. But if any of you are interested in being in on the really ground floor, maybe even the basement floor, stay tuned to what's going on with this project, because you will have opportunities to get involved, and there are stipends. So one thing that came up actually at a meeting today was, well, what if teachers want to be involved now? What if we've got some of you guys out there that are already coding with your students and you think, you know what, I'd like to use your curriculum, and I'd be willing to give you some feedback on that. So is that a thing? Is that a possibility?
I definitely see that I could do something like that. I would like to do look at some of the curriculum and see if we could throw it in here and there in the classroom that I'm teaching now.
Okay, and you feel good about coding? You know about coding yourself and wouldn't feel...
Yeah, I've done coding before, never on Pirate, but I don't think it would be too hard to pick up.
It's not that hard. It's not that hard. And so on my screen, you're caller 2. But could you tell me your name?
Oh, I'm Patty, Pat White.
Okay. Oh,
yeah.
Okay. So you're going to be there this summer?
Yes, I am. Yeah.
Okay.
And I've done coding with my students in the past with VPython, but this looks like this might be more doable. I just need to check it out.
It's pretty simple. It really is pretty simple.
Yeah.
And you can get a free account if you go to I think it's code.pirate.org.
Yeah.
But we'll look again. All right. So if anyone is interested in being involved, again, you've got my email address on that last screen, and email me. Or if you have any kind of interest in knowing what's going on, be in touch. It's 5 o'clock. Shoot. I'm just going to very quickly show you what the team of developers last year decided were the underlying concepts of integrating computation into physics. These are the things that we're focusing on as the computational concepts. So, and they also kind of point at when it's a good idea to have a coding assignment for students. So if something repetitive is going on, that's a good place to do it. You know, understanding the repetitive nature of simulations, the role of parameters and data types, program execution, and then this was huge for all of the teachers all the time. We have our monthly check-ins with them, and every single time we spend most of the time talking about errors and how students deal with errors and how they have evolved ways of thinking about approaches to handling error interpretation. So this has been a really big issue. And then defining physical variables and connecting them with the world, because that's a big step that wasn't happening with computer science teachers. It was happening with physics teachers in the workshop last year that everybody was kind of interested in. And then we have a computational modeling cycle. So this also very preliminary, and anybody who wants to see this, email me. I will send it to you, but we love feedback on this. This is what we came up with last year. It's a first draft. Just like writing code is a first draft, and you know, you click the run button to see if it compiles, and you know, nobody expects it to compile the first time. And that was hard for kids to get over that hump of, oh, when I'm done writing the code, I should be done, and I'm going to click the run button and it's going to be done. But no, it's not. It's the beginning of the next step, which is error checking and debugging. So, so this is our computational modeling cycle, and that's pretty much it. I will hang around and take questions. Oh, this is a little, why did we choose Bootstrap? And really, we chose it because we need a lot of support, and we get it from these people. It's interesting to work with a team of people that are actually rewriting the language to support your needs as they are teaching it to you. This was a really valuable thing for us last summer.
Colleen, I do have a question.
Yeah.
Is there anything built into the current curriculum where you connect I think I just saw you mention this, but where you connect the student's model to a physical experiment they're doing? For example, have them create a model for projectile motion and use that to predict the actual landing point for a projectile in the classroom in the lab?
Yes, we do that. We have them, sometimes they do it in lab first and then they code it. Sometimes they code it first and then they do it in lab. But we do both of those things.
Very nice.
Yeah. So I'm going to take a moment now and show you the other little bit of code. So that was a student code that I showed you. This is code written by a teacher that is in lieu of a lab because, come on, load up. Okay, because most schools don't have access to 9-story elevators. So this is an elevator problem code. So yeah, Josh Rutberg wrote this. We will run it. And what is it that I type? Shoot. Run simulation. And here's my elevator. And so I'm going to hit my number key. I hit the number 1 and it goes up to the first floor. And now it's going to go up to the 4th floor. And now it's going to go up to the 8th floor. And then it's going to go down to the basement. And so when I stop, look at what I get over here. I get an output of every 400ths of a second, I get an output of position, velocity, and so on. And you can take this, you can copy it into Augur Pro if you want, or Excel, or whatever graphing program you use, and you can compare. You can look at multiple graphs simultaneously, and it's really very cool. So this allows you to do that, get on the elevator with a bathroom scale virtually instead of finding a 9-story building and having a field trip. And oh, I see in my window there, I believe Pirate is free. Yes, it is. Pirate is free. So, questions? Comments? Feedback?
So do you guys not have any available curricula or units?
We haven't shared them yet with anybody because they're still rough, and we promised the teachers who were there last summer that we would not share them yet.
Okay.
So I expect we will have things that we are willing to share upon request. We're not going to post them quite yet on the website, on the AMTA website, but I think that if people give us, if people say, I am willing to test this for you and give you feedback, then we will be willing to share. Oh, and I see a question about, can students use this to write an app for their smartphones? Not Pirate. No. Any other questions I can answer for you?
I like the ability that it's inbred into the curriculum. I like that because it's not like taking time out as separate. This is going to be very interesting to see how, if I can get it up on the computers at school, so that's my next step. But I really am excited.
That's actually the biggest barrier to implementation that we've had this year is, so the nice thing about Pirate is that it's web-based. You don't have to have anything installed on your computers, and the only real barrier is that some schools make it so darn difficult for kids to reach the internet.
Right.
And then there was one other big issue at one school where they didn't actually have computers that were internet capable. The faculty could have computers that were internet capable, but the few laptops that they had for students weren't wireless.
Wow.
So they had to actually buy wireless laptops and install a router, and then they realized they cheaped out on the laptops, and the radios weren't strong enough to get the signal from the router. So that school has just had technology nightmares. It's really, I think, necessary for your administration to, to give you the seal of approval on doing this with your students so that they make the tech people meet your needs.
Right.
Other questions?
Yes, I have a question or maybe a comment. I'm one of the physics first teachers, and One of the things we've been trying to sort of pilot is a combination of robotics with coding with physics, where we, for instance, program a robot to do some sort of motion and then be able to modify that motion and be able to follow that motion using sensors and things like that as a way to kind of reinforce the, just sort of the whole idea of motion and acceleration, et cetera, et cetera. Is that along the same lines of what you're thinking about trying to do? Because we're interested in sort of combining the whole idea of robotics with coding and physics.
Well, we have not actually tried to do physical computing with this coding, but there are a number of teachers who are using this right now who say their kids are in robotics. You know, they're in a robotics class or they're in a robotics club, and they tell us that the kids prefer coding on Pirate to coding in the language that they're using for their robotics. So I don't know whether there's just more control or, I don't know. They prefer using Pirate.
Yeah, I guess I'm thinking more of, again, being physics first and dealing with a wide range of abilities. That certainly sounds like something from a student who is a high achiever. I'm thinking about more of getting those students who are maybe just peripherally interested in coming up with ways to get them a little bit more interested, in physics and robotics and in coding. I think all these things would be great for, the very upper level kids. I'm again more interested in trying to apply it to the average kids or even below average kids, just to see if we can't get them to be more in tune with the physical processes that go on with motion and energy and the whole gamut.
Well, I think actually that's a really good question, and I need to take it back to the Bootstrap people and find out what whether or not that's a possibility. But the coding that they do, and what I showed you that the student did was pretty elaborate compared with where they begin. And I know that I used to have a physical computing workshop that we did where we would just, have these little robots and we would make them, we would program them, or the kids would program them to try and run a maze. And this is certainly in the same, this is in the same ballpark. But right now, the outputs for Pirate that we are using are just, screen outputs. So they're programming simulations basically, or they're programming, something dynamic. They're making something dynamic happen on a screen.
Okay, thank you.
Sure. Other questions? How's the weather in New Jersey? I see we have someone from Newark.
Yeah,
We had all
crazy.
rain today.
I'm in northeastern Jersey, and it's 2 feet of snow here.
2 feet of snow.
Wow.
Yeah.
Wow.
And I'm in South Jersey, and we got poured on, so.
Huh. Okay, well, I guess we know where the boundary of that storm is.
Yeah.
All righty. Well, thank you all for coming.
Thank you for inviting. We appreciate it.
Stay tuned. Interesting things are going to happen.
It's exciting.
Thanks, Colleen. Take care.
Thanks a lot. Good to hear from you, John.
You too. Thanks.
Okie doke. Wendy, I think we're done.